Uh, Good morning, everyone. Distinguished ladies and gentlemen, welcome to Physics 121 class, which is a faculty-based course. Uh, Two of us are assigned to teach this course. Myself, Zubairu Abdulmini Loko, and Dr. Ibrahim Inusa Ewa. We have actually shared the content into two. I will be taking part and he will be taking the other part. Now, just by way of sharing with you the content, we shall be covering, including me and him, we will be covering this area of concern: electricity, magnetism, and modern physics, which is a course title, and it's called Physics 121. The areas or topic under it includes electric charge, Coulomb's law, electric field, electrostatic potential, energy in an electric field, capacitors, dielectric, electric current, potential difference, electromotive force, Ohm's law, potentiometer, meter bridge, Wheatstone bridge, magnetic effect of current, permanent magnetism, Earth's magnetic field, Faraday's law of induction, generators and electric motors, alternating current, Maxwell's equation, structure of the atom, radioactivity, X-rays, application in life sciences, nuclear energy, and so on and so forth. Ladies and gentlemen, this is the area that we'll be covering by way of introducing the course. For the first course contact we are meeting, I will be covering this area: electrical charge, Coulomb's law, electric field, electrostatic potential. Now, let me give you some background of the subject matter. I want to believe that all of us know what is lightning, or understand what lightning and thunder is all about. I think during rainy season, sometimes you see a kind of sign of light that strikes the earth, and at a point after the lightning, you see thunder follows. Lightning and thunder are two common phenomena in our hot and humid atmosphere in Nigeria. Have you ever given a thought to what is responsible for the occurrence of the phenomena? Now, let me give you life experience. At about 1 month or 2 months ago, to tell you how dangerous this lightning could be. While while it was raining and the weather was cloudy, what actually happened was I was receiving call while my phone was plugged directly to charging point. And when thunder and light strikes, believe you me, I receive a serious shock. And that is how dangerous some of this thing is. And that is why in most cases it is advisable that whenever it's raining, whenever the cloud has changed, please unplug all most of your electrical appliances. At home, sometimes if you don't have guards that is plugged to your socket, at the end of the day, when thunder strikes, it will affect most of the appliances at home. So this is how effective, or this is how dangerous some of these things could be. So you are advised to unplug most of your electrical or all electrical appliances while it's raining, or if the cloud has changed. Now, moving further, a physicist, Benjamin Franklin, demonstrated as long ago as 1752 that thunder clouds are charged with the term of electricity. All of us are very conversant with electricity, and once electricity is mentioned, what comes into your mind is NEPA. However, just like what we have done in Physics 121, for those of you that were part of the class, right, you have different forms that can be transformed to electricity energy, types of energy. It can either be sound energy, light energy, electricity energy, kinetic energy, and so on and so forth. These charged clouds, when discharged in the atmosphere, give rise to a great spark, which is referred to as lightning. It will interest you to know that the amount of electric current during the discharge is about 20 kilo ampere. That is 20 times 10 to the power of 3, which is approximately 20,000 ampere. Are we together? Now, electric charge continue. The electric discharge, which gives rise to lightning, also produces a great amount of heat. In a fraction of second, temperature rises to about 15,000 degrees Celsius. The lightning develops in a small area which is about 20 centimeter in width. However, as a result of heat, amount of grades produced in that small area, the air molecules move fast and causes the intense sound which you call thunder. So you see, that is the background or what gives rise to what we call thunder today. When the sound is reflected by cloud, hills, or any other obstacle, we hear the roaring of cloud. A very important thing about electric charge is that the forces between them are very large. Therefore, the force is known as electrostatic force or electric force, and is responsible for holding electrons to nuclei to form atom, and for holding the groups of the atoms together to form what we call molecule, solids and liquids. The study of these static changes is known as electrostatic. Indeed, electrostatic was the first branch of electricity to be investigated, and for some time it was regarded as a subject which had no practical value. However, it is now known to have a practical industrial application. For example, we shall see later in this course that a knowledge of electrostatic is important in the design of cathode ray tubes for television, in electrical prospecting minerals. Electrostatic loudspeaker and microphones are in common use, as well as electrostatic photocopying machine, which actually produces light. That is what you use in photocopying today. The ancient Greeks discovered that amber, when rubbed with silk, acquire the property of attracting light objects such as pieces of chaff. William Gilbert discovered that other substances exhibit the same effect, and that the magnitude of the effect is roughly proportional to the area of the surface rubbed. He was then led the idea of charge of electricity. Dufay in 1945 discovered that there are two kinds of electricity. Two ebonite rods, when rubbed with 4 exert a force of repulsion on each other. Two glasses rod rubbed with silk also repel one another. However, an ebonite rod which has been rubbed with 4 attracts a glass rod which has been rubbed with silk. Any substance rubbed with a different substance acquires charge of electricity, and is found either to repel charge, ebonite, and attract charged glasses, or vice versa. And that is why in most cases we will say like charges repel, unlike attract. Since the two kinds of electricity can neutralize each other effects, one is called positive and the other is called negative. Note that the choice as to which is positive was purely arbitrary. Glass rubbed with silk is said to have a positive charge, ebonite rubbed with 4 a negative charge. Now, let me also give you an insight of these charges that we are talking about. You remember when we were small in primary, secondary school, we cut up pieces of papers as small as they are, and we use the biro we use in writing. You rub your hair when you rub it deeply, you understand. And if you come and place it in these small pieces of paper that you've cut, you will find out that you see how magnetic the pen is trying to pick these pieces of paper. This is the concept behind what we call charges today. Now, the origins of positive and negative charge of proton and electron. The law of force between charges may be stated as follow. Like charges, just like what I've just said earlier, like charges repel, unlike charges attract. Let us now understand clearly the origin of two types of charges. We remember that an atom consists of positive charge nucleus with negative charge electrons around it. The nucleus is made up of proton and electron, right? Your chemistry knowledge. The neutron is neutral or no charge, which the proton and electron have equal but opposite charges, positive and negative. The proton and neutron is a nucleus. In the nucleus are held together very tightly by nuclear force. So strong is the nuclear force that the proton are unable to move away from the nucleus. On the other hand, the force holding electron to the atomic nucleus is much weaker than the nucleus force. Hence, the electron may move away from the atom. When two different materials are rubbed together, the electron gets transferred fairly easily from one material to the other. Since some material tends to hold their electrons more strongly than others, the direction of transfer of electron depends on the quality or depends on the material. For example, when a plastic ruler is rubbed with a wooden cloth, electron flows from wool to plastic so that it carries net negative charge, whereas the wool with a deficit of electrons carries the positive charge of equal magnitude. And also, to get you more clear or to inform you more, you remember sometimes, or in most cases, especially for the guys, even for the ladies, if you wear one kind of clothes, trying to pull it through your head, if you are rubbing it, you feel some charges from the hair to the cloth. And this is just a clear terms of this example of charges. Are we together? These are example, more clear terms of these charges. Now, the process of changing the bodies by means of rubbing them together is called changing by friction. In any case, we should note that friction actually has nothing to do with charging processes. It will appear that friction is only borrowed to describe the rubbing process. Now, charge, the unit of charge is the coulomb, where one coulomb is 1 ampere per second, and one coulomb is equal to 6.24 times 10 to the power of 18 electron. The coulomb is spelled as Coulomb, is defined as the quantity of electricity which flows past a given point in an electric circuit when a current of 1 ampere is maintained for 1 second. Thus, charge, which the unit is in coulomb, is written as capital Q and is equal to the product of current and time. That is, Q is equals to I times T, where I is the current and the unit of current, which all of us are aware is in ampere, and T is the time, which is in second. Now, ladies and gentlemen, we know that the time usually is in second. In a situation whereby I only want to draw your attention on something. Sometimes we will give you question to truly, and that is why they call it examining, or to give you, to test your understanding by way of assessing you. If I give you time in hour, it is expected of you to convert it to minutes, and you convert it to second. Or if you are given time in minutes, you are expected to convert it to be in second, and that is the basic or the beginning of time, measurement of time, and it's surely in seconds. From second you have minutes, from minutes you have hour, from hours you have days, and so on and so forth. Please, you take note. In most cases, sometimes if you are given time in minutes, some people will just calculate the they will do the calculation without doing the conversion. So it is expected of you to take note. Assuming I say 2 minutes. When I say 2 minutes, you should know that you need to multiply 2 by 60, because it is 60 seconds that give rise to 1 minute. And for you to have 2 minutes, you multiply the 2 by 60, and that gives you 120. And that should be the value that you'll be using in doing your calculation, not the 2 minutes. Are we together? Now we have an example to illustrate what I've just said, that if a current of 5 ampere flows for 2 minutes, you should determine the quantity of electricity transferred. We know quantity of electricity or charge, which is Q, is equal to the product of current and time, and the unit is in coulombs. I is given to us from the question to be what? 5, and time is 2 minutes, and that brings us back to what I've just said. That's 2 minutes. You need to convert it to second. You multiply 2 by 60. That gives you 120 seconds. Hence, Q is equal to 5 times 120, and that gives you 600 watts. Do not forget, anytime you are making your calculation in sciences, unit matters a lot. And that is why, for those of you that have attended Physics 111, that is the beginning of the course, so that you understand how important attaching unit. But by the time you write, okay, 5 times 120 is 600 naira or $600. By the time you indicate the unit, you are communicating to whosoever that is reading that yes, you understand the subject matter. Are we together? The unit of force is the Newton, where 1 Newton is 1 kilogram meter per second squared. The Newton is defined as the force which, when applied to a mass of kilogram, gives it an acceleration of 1 meter per second squared. Thus, we are very much aware that force, that is, which is in Newton, is equals to the product of mass times acceleration. Now, let me digress here a bit. You remember the laws of motion. One of the law states that an object will continue to remain in a state until until an external force is applied. Let me take, for example, this is an object. This departmental handbook, assuming, let's take it as an object, which it is in real science. This thing will continue to remain in its position until I use the force in me, and I've shifted it or moving it from the position it were to another position. And that shows that law of motion applies. That is, the object has, force has been applied into the object and it has changed its original position. Is that clear? Now, that also brings me to, for you to understand the concept of force or the concept of a motion that deals or that revolves around a force, for example. Now, if you are dealing with a linear motion, that is motion that is moving within an x-axis, that is, movement of the motion has to do with horizontal movement. This is where this force is going to be applicable. F is equals to the product of mass and acceleration. However, if the motion is moving in a vertical form, assuming, for example, for an aeroplane, the movement of an aeroplane, it moves from ground, it moves vertically, isn't it? And if I may use that, you see, let me take, for example, this object in my hand, and I want to apply a force by moving it in a vertical direction. You see, by the time I throw it up, what happens? It reaches a point where the force that I use in sending it up can no longer be applicable, and there is what we call gravitational force. The gravitational force now will take effect from where the force I have used in sending the object up. From there, it will start coming down. Instead of it to continue going up, it will start coming down. Are we together? Just like in the popular saying, And Hausa man will tell you, "Durni san dutse kasa zai dawo." It means the force has a limit to where it can go. So it will, gravitational force will be applied, then it will start bringing it down. Also, I think, according to one of my lecturer, that 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 one Professor Oyibo from Kogi State. Let me finish this concept before I finally give you the story behind the force. Now, by extension, if it is a movement that has to do with the vertical movement, in this case, that is on y-axis, in this case, A will now change to G, where we have a constant value of gravitational acceleration, that is equals to 9.81 meter per second square, or approximately you make it 10 meter per second square. As such, even if the question come in a way that the value of acceleration is not given, you should know or have it at the back of your mind you are dealing with acceleration due to gravity, and the question, by way of description of the question, will now direct you on how this will actually work, so that you can perform your analysis by way of computing the value of force or computing the value of mass, as the case may be. Are we understanding? I hope I'm not talking to myself alone. So, ladies and gentlemen, moving further, we know that m is the mass and the unit of mass is in kilograms, and a is the acceleration. I told you that the acceleration a can change to g, to acceleration due to gravity, right? In meter per second square. Gravitational force, another name for gravitational force is what we call weight, and the formula will be F is equals to mg, where g is equals to 9.8 meter per second square, or 9 meter second to the power of negative 2, as the case may be. I think we are learning. Are we learning? Now, I have an example. A mass of 5,000 grams is accelerated at 2 meter per second square by a force. Determine the force required. Now, you see, I told you that question might come in a form that require you to do some little adjustment or conversion, so that you can perform your arithmetic easily. Now, if you look at it, 5,000 grams, and you know that the unit of mass is not in gram, it is in kilogram, and you have gram. For you to obtain the value of mass, which is in kilogram, you need to convert 5,000 to kilo. In doing that, you divide 5,000 by 1,000. If you divide 5,000 by 1,000, that gives you what? 5 kilogram. It means by extension your mass is 5 kilogram and your acceleration is 2 meter per second square. By the time you multiply mass times acceleration, which is 5 times 2, that gives you 10. And the unit of force, which we have said it earlier, it is in Newton. It means your force is equal to MA, which is equal to 5 times 2, and is equal to 10 Newton. Are we together? And that is just the example we've illustrated. Moving further, that you should determine the force acting vertically. Now, this brings us about the illustration I have just given earlier. When you are dealing with a vertical movement, downward or upward, as the case may be, right? I tell you that has to do with gravitational force on a mass of 200 grams. Yet again, you need to convert 200 grams. You divide it by 1,000. 200 divided by 1,000, that gives you 0.2 kilogram. It means your mass is equal to 0.2 kilogram. Your acceleration, even though not given, but you are dealing with gravitational acceleration because the movement of the object is in vertical direction. As such, your g is equal to 9.81 meter per second. Therefore, mass acting downward, which is, I told you that another what do you call, another name for gravitational force is called weight, right? Which is equals to mass times acceleration, and you have 0.2 by our conversion multiplied by 9.81, that gives us 1.962 Newton. Are we together? I believe everybody is understanding. Now, moving further, by digesting further, work, the unit of work, which another name for work is energy, is in joule, where 1 joule is 1 Newton meter. The joule is defined as the work done or energy transfer when a force of 1 Newton is exerted through a distance of 1 meter in the direction of the force. Thus, work done on a body, the unit of work done is in joule. Work done is equals to force times distance, where F times S, where F is the force in Newton and S is the distance in meter moved by the body in the direction of the force. Energy is the capacity for doing work. Now, I feel it is important for us to bring about power. The unit of power is in watt, where 1 watt is 1 joule per second. Power is defined as the rate of doing work or transferring energy. Thus, power, the unit of power is in watt, is equals to work all over time. It means I can as well say power is equals to force times distance divided by time, because we know by the explanation above, we know that work is equals to force times distance. Where your force is given to you and your distance is given to you, it means instead of using work, you can substitute it with this value. In any way, it depends on the parameters that are given to you, where W is the work done or energy transfer in joules and T is the time in seconds. Thus, energy in joules, which is equals to work, is equals to, and I can say work is equals to P times time when you make W the subject of the equation. Now I have an example that a portable machine requires a force of 200 Newton. It means F is equals to what? 200 to move it. How much work is done if the machine is moved 20 meter, that is the distance? Now you have force, you have distance, which is S, and what average power is utilized if the movement takes 25 seconds. This is a further calculation, but we know work is equal to force times distance. You multiply 200 by 20, that gives you 4,000 Newton meter, or if you convert it to kilojoules, you divide it by 1,000, it makes it 4 kilojoules. But we know that power, which is the average power we are asked to calculate, equals to work done all over what? Time taken. And 4,000 by the calculation divided by 25, which is equal to 160 joules per second, or 160 watts. Ladies and gentlemen, these examples are very straightforward. You need to practice for you to understand. In a situation whereby you don't practice, sorry. Now, moving further, work done is equal to force times distance, which is another example. I believe you can go through where you have a problem anytime we meet in the class for physical mode. Come up with your questions, get examples, and solve as much as you can when you come so that we can discuss. Now, electrical potential and EMF, the unit of electrical potential is volt. Now, you see, electrical potential or voltage or electromotive force or potential difference, they can be used interchangeably. Where 1 volt is 1 joule per coulomb, 1 volt is defined as the difference in potential between the 2 points in conductor, which when carrying a current of 1 ampere dissipates the power of 1 watt. Volt is equals to watts divided by ampere, or joules per second divided by ampere, or joules per divided by ampere second, or joules divided by coulomb. A charge in electrical potential between 2 points is an electric circuit. In an electric circuit, is called potential difference. The electromotive force provided by a source of energy such as a battery or a generator is measured in what? In volt. Now, ladies and gentlemen, we'll be stopping here for today's class. Please, I advise for those of you that will be listening to this virtual mode, kindly go through the material, study it very well, identify areas you are lacking when we come for physical mode, so that you can be able to ask questions and be clarified. Ladies and gentlemen, this will bring us to the end of this class, and we'll be seeing in the subsequent class. Thank you very much for listening.